I'm Jason Biggs. I work for Wolfram Research, and I am the lead developer for the chemistry functionality in Wolfram language. And so this talk is about the molecule introduced in version 12, as well as some of the enhancements that are planned for 12.1 and beyond. All right, my name is Jason Biggs. I've been a chemistry developer here at Wolfram Research for the past 3 years now. And I'm going to show you, this is my third time giving a talk here, and so this will hopefully build a little bit on the previous talks, but also show some new stuff. Let's see, so brief outline, right? So I'm going to briefly talk about what has been chemistry in the Wolfram language up until version 12. I went more in depth in that last year, so we'll just kind of try and fly right through that. We'll talk about the molecule, which was introduced in version 12. It's a new computable data structure. We'll look at some import-export. One of the features for 12.1 that we're working on is to update the number of formats that you can export a molecule from and import a molecule into. A brief preview of some post-12 functionality. And then I have a couple of more in-depth applications, which, if history is tells me anything, then I'll be too late to even get to those. But hopefully not, because I think they're interesting. And then I would like to plug the second talk from the Wolfram chemistry team that takes place today at 2:30 in the fighting in this very room, stepping towards chemistry mastery, about the continuing efforts of step-by-step in chemistry and Wolfram Alpha. All right. So let's see, from chemical data to entities and beyond. So starting in version 6, we had chemical data, which was is what we like to call curated data, right? So when you installed Mathematica, you would have there in the layout these files that contained all of this data that was curated by people who work in Wolfram Research from sources such as NIST, PubChem, ChemSpider, chemical abstracts. And so the way chemical data works is that there has to be data in the packlet. It has to have been curated. So you say chemical data, I want propane, give me the combustion heat. And so it'll return the value because we have the value there. And so likewise, you can ask for the van der Waals constants of isononyl peroxide. And also we have thermodynamic data, which allows a little bit of computation. So we have entities in thermodynamic data. You can ask about the molar isobaric heat capacity and provide a temperature, and it can compute that. So that was introduced in version 6. This was extended to include not just chemical entities. There were elements, there were minerals, there were cities. And so a new framework was needed to deal with arbitrary types of entities and properties about them, and that's where entity value comes in. So for entity value, you have these things which you've seen in other talks, which we call them yellow boxes. This is a random chemical, and this is the same. It draws on the same knowledge base, the same information base as chemical data, but it's more easily updatable. And it's a more cohesive framework. So in an entity value, you have classes of entities. For instance, greenhouse gases gives you a list of all the chemicals that have been curated into the category of greenhouse gases. You've got lots of properties, and you've got an accessor function entity value, which allows you to take entities and properties and get the information in a nice and computable, presentable form. So we've also got service connections. So for things outside of the knowledge base, things in other external databases, like PubChem. So you can create a service connection to PubChem, and this returns a service object. You can then query that, give it some type of identifier to represent a chemical, in this case chlorine dioxide, and you can ask for the compound description. And it returns this nice data set of all the information available on PubChem. Likewise, we introduced the Wolfram data repository, which allows not just the curators at Wolfram Research, but anyone to submit their own curated data. And so, for example, these are three external data sets that were turned into entity stores. And so this is a way to extend the knowledge base. So this is the GDB9 database. And if I click on this, it'll take me to an external web page that gives me information about that data set. But if I call resource data GDB9 database, then it gives me an entity store, and I can access it using the very same framework that I just described, the entity value. So there are properties and entities, and you can query for the values and present them all in a nice data set in the same way. And there are more of these data sets. And then there's also Wolfram Alpha, right? You can access it on the web or within your notebook. You can ask natural language queries like how many carbon atoms and 5.46 kilograms of propane. And you can ask for the pH of 2 molar acetic acid. Likewise, you can, Likewise, you can look up the step-by-step to figure out the percent yield for a given chemical reaction. But I'm not going to talk too much about the step-by-steps because that's for the talk today at 2:30. So with version 12, we have the molecule. A molecule allows you to create an object that represents a chemical species. And so the molecule, it doesn't rely on the external database. It doesn't rely on a connection to entity value. It sits in your notebook, and it's created on the fly. When you say molecule of water, it creates this molecule. It's composed of atoms and bonds, so you can get its atom list or its bond list. Or actually, you can just look at it, just like any other Wolfram language expression, you can ask for its input form. And you'll see it's a molecule. It has the head molecule, a list of atoms, a list of bonds. And so you can have more complicated ones. Molecule L-alanine. I always pull this one out as an example of a molecule that has stereochemistry. So this L, when I say L-alanine, it describes the 3D arrangement of the atoms. It tells you a little bit about the stereochemistry of that molecule. So we can ask for the input form. And so again, we have a list of atoms, a list of bonds, and some stereochemistry elements that tells me that if I look at the atom represented by number 2 in this atom list, that the ligands around it, the other atoms that are attached to it, when listed in this particular order, go counterclockwise. Such things are actually very important in chemistry, and so finding a way to represent those computationally is important. So you can ask for molecule properties in much the same way that you can ask for properties of entities, except for in this case, they're computed on the fly. They're not stored before you ask for them. So you can ask for the molecular mass, the point group. You can make changes to the molecule. If you take your molecule, you can set the mass number. And so in this case, we took water and we turned it into D2O, or heavy water. Yeah?
Sorry, on the properties that computed on demand, so for example, the point display, instead of specifying molecule water, I can presumably specify molecules using the atoms and the bonds.
Yeah.
And would that actually be
right? So if you don't supply coordinates, then we need to create coordinates. And so there's a nice algorithm built in that will use. So I can talk more about the algorithm that generates those coordinates. But so it generates coordinates, and then we use a force field to try and minimize them, and then we can return the point group.
But I can also specify coordinates.
Yeah, absolutely. And you can bring in your coordinates from an XYZ or an SD file. Let's see. So there's ways to visualize the molecule. So I can create a molecule and I can make a 2D and 3D plots of it. If I want to show the hydrogens or if I want to hide them, typically, so can everybody see? I put this up to 150%. Okay, you might not see the little H's or whatnot, but when a chemist makes a drawing like this, it's understood that even though there's no C here, that's a carbon. And it's understood that even though there is no hydrogen listed right here, that because that carbon has a double bond and a single bond, in order for it to be a neutral molecule, there is a missing hydrogen. And so in order to draw less cluttered diagrams, we will typically omit those. And so, but you can control that via the plot theme or via the include hydrogens option, which I'll get to it on down. So likewise, there's a molecule plot 3D with its own plot themes. You can do the typical ball and stick. You can omit the balls for the atoms altogether, or just use those, represent the atoms as spheres with the van der Waals radius. You can highlight in atoms. So if I say I want a molecule plot of M, which is defined above, and I want to highlight atom 9, and I want to highlight this particular bond, and then I want to highlight all oxygen atoms, then I can do that. And the colors are chosen automatically. If I wanted to provide my own color, then I could wrap these in style and provide a color. So this I'm always impressed by this, so I always try and throw this into the talks. So in order for chemical names can be rather long and descriptive. So the whole point of an IUPAC name is to systematically tell you, just using text, what the 3D structure of this molecule is going to be. So in this case, so the rules for these are dictated by the blue book and the red book. Imagine I had a little bit of dynamic there, so they popped out. But okay, so for a name like this, we have 2,3,3-trichloro-prop-2-enoic acid. So what that means is with the base, we have an enoic acid, or let's see, enol-oic acid, and then 2,3,3-trichloro. And so, this is, all of that structure is encoded in the name. And when I say molecule of this name, that is decoded and turned into what's called a SMILES string. And from that SMILES string, we build the chemical graph. Likewise, 1,3,3-trimethoxy-prop-1-ene. So prop-1-ene, right? And then you've got trimethoxy, and the 1,3,3 says where those 3 methoxy groups live. And likewise, we can do a big name like this, and I'm not going to walk you through that one. But, I mean, that's the cool thing, right? So you've got companies that have been around for 100 years, like Chemical Abstract Services, whose whole job is to take molecules that chemists make in the lab and find out what the proper name for it is. And there's science to that, but that is definitely an art. But then once they've done that work of making the IUPAC name, coming back out to the structure, well, that can be done algorithmically. And so I'll show this on the very last slide, but this is done via the Opsin library. It's a phenomenal library, and it's included. It's not, when we do this, it doesn't make any call to the knowledge base. I could have turned off the internet, and it will just do it using the what's included in the layout. No, so that is a much harder problem, and to do that algorithmically, I'm aware of one commercial solution that does that, but yeah, it's a harder problem. Let's see. So I mentioned properties. So once we create a molecule, we can get the molar mass on the fly. There are a whole host of properties. So in order to discover them, the autocomplete is great. So here I've got molecule value, and then let's see. So these don't scale as well with the 150%. But if I just scroll through this, I can see all the different properties that can be computed, right? I can get the bridgehead atom count, for example, which would be the number of atoms that bridge a ring. And so if you want to look at all of those properties, you can create, they're grouped into different types of properties, right? So general properties, geometric properties, which includes the Coulomb matrix, interatomic distance, principal axes. Yeah, and so they're easily discoverable in that way. And yeah, so I think that's about all for that one. Right, so molecule patterns. So once you have a molecule, so you might want to look inside that molecule to see, does this molecule have a carbon atom? Does this molecule have any cations? Does it have anything with a ring? And so we've got an expressive language for that, for describing patterns, right? So here's a list of patterns, one that represents an oxygen, one that represents any atom with a formal charge greater than 0. And so I can take those and I can make an association where I give a label to the pattern, and I can just put that directly into molecule plot, and it'll highlight and show me the oxygen atoms, the cations. So here, what do I have? TNT, right? And so, yeah, it works very quickly. You can do the same thing with bonds, right? So in this case, this is a pattern for a nitrogen-nitrogen bond, a pattern for any type of a halogen bond, and then likewise, I can just give those to molecule plot and find the pattern inside the molecule. If I want a bigger pattern, more than just a single bond or a single atom, we have a data structure called the molecule pattern, which is like a molecule. It's got a list of atoms, which can be patterns, right? So this is one with a heavy atom coordination number greater than 2. So that means an oxygen atom that's bonded to 2 other atoms that are not hydrogen. And so that's here highlighted in yellow. So this is our carbonic ester. Okay, so now we come to import-export, right? So we've got various formats that have been around in the system for quite some time. When chemical data came out, we were able to import things like XYZ files or PDB files and create graphics out of them. Well, now when we import them, we can create a molecule, right? So with a SD file, this is one of the more widely used formats around now, right? So it allows you to store 2D or 3D coordinates and an arbitrary set of properties. And new in version 12, we have much faster access, right? So I have this particular SD file that I downloaded. Seems to be some patent data. Patent mining is a big area in cheminformatics at the moment. And so you'll find these SD files, and this one has 275,000 molecules, right? And so how long does it take it takes just, let's see, last time I ran this, it only took 5 seconds to figure out that there were 275,000 molecules in it. And if I want to, I can access those without reading the whole thing in. So before version 12, if I wanted to have just the 200,000th molecule, it would read in all 275,000 and then just pull out the 200,000th. And so in this case, it doesn't do that. Here, what I'm asking for, I'm saying, give me the first through the 200,000th in steps of 5,000. And when I ran that before, it took 5 seconds. And then at the end, we have 40 molecules. And so that's a big improvement. XYZ files. Now this is a tricky problem, right? So when I take a molecule and I export it as an XYZ. So let's start with this. Let's make that, and then let's export that as an XYZ string. So all you have in an XYZ file is the list of atoms and the list of coordinates. You have no bond information. And so the problem then, for importing it, is what we call connecting the dots. If we want to import it, we have to know that there were bonds between which atoms, and more than that, we'd like to know what kinds of bonds they are. And so that's gotten a lot better. That will get a lot better in 12.1. In 12, there were some cases where you would import something from an XYZ file and it would have bonds listed as undefined. So we're improving that in 12.1. So in this case, I export it as an XYZ, and then I import that same thing back to a molecule, and it turns out to be the same molecule. We've always had CIF importing. So if you import a CIF file, you get this kind of information. This is generally useful for solid state type of chemistry, which is not my forte. But now you should be able to import that as a molecule, in which case you take the fractional coordinates provided in the file and convert them to Cartesian coordinates. And you also get some meta information about the unit cell. Likewise, we're going to have import and export for hyperchem format, which I don't think it's all that widely used. So let's not talk about that. Yeah.
Sorry, on SIF, should we expect, this is all amazing, should we expect the solid function?
So I've heard people ask about that, right? And so that, so please come on Wednesday. So I'm having one of the round tables at the lunch. And so essentially, I don't know very much about solid state chemistry. And so I could imagine there being a data structure that is that has the head unit cell. And I could imagine plotting it, right? And just saying how many unit cells you would like in the plot. But other than that, I don't fully know what people would want to do with it. More towards where I come, my background is the formatted checkpoint file, right? So this is produced by the Gaussian software. So if you've run some calculations and you end up with a formatted checkpoint file, you can now import it. It contains 3D coordinates, but then it also has a lot of other meta information about the orbitals and the energies. And then the more flashy of the new formats would be the cube file. Right, so this is volumetric data, right? So if I look at the first few lines of one of these files, it tells me about a grid that that it's giving me. It gives me the XYZ coordinates and the atomic numbers and masses for all the atoms. And then it just lists number after number, and it goes on and on and on. And essentially what that is it's giving me all the value of the electronic wave function or the electronic density on each of these grid points. And so then the goal is, when you import it, you'll get back a molecule. If you look at its meta information, then it's going to have this volumetric data, right? So it'll have all of the that data from the cube, but then it'll also tell you the range, which you could then plug into list contour plot 3D, or you could just import the graphics 3D element, right? And so you could get these nice plots. And here's one that shows not a wave function, but the electronic density. So when that says 2 minutes left, what does it mean? It really means it, okay. Okay, so just a few of these toy little functions that I've been working on here, right? So we've got resonance structures. What this means is when you look at ozone here, it has a double bond on one of these and a single bond on the other. Well, that's just because when we describe these as a chemical graph, as a molecule object, we have to assign a bond order to every one. But in reality, it's some combination of the two. So resonance structure list will expand that out. So likewise for benzene, right? It's not just this is the double bond, this is a double bond, this is a double bond, but it's in resonance. There are these two structures that occur at the same time. We've got tautomers, which are different than resonance structures. Tautomers are actually distinct species, but they can readily interconvert amongst each other in different environments. So in this case, you've got isocyanic acid. This hydrogen can move from this oxygen all the way to the other nitrogen. And we call them a mobile hydrogen. Likewise, for a phosphonic acid, right? You can have this the hydrogen move from one of the oxygens onto the phosphorus, which is why this is a diprotic acid and not a triprotic acid, which you might think it would be. And then if you take something like this molecule, which I don't have its name, then we can find 375 tautomers. And like I said, I'm going to have to skip over the applications, but I do want to touch on molecule recognize, right? So you have this image, and it's got a head of image, and we can convert that directly into a molecule by using optical character recognition. Ha ha ha, I'm out of time. Likewise here, right? So I can do molecule recognize of this, and it becomes this molecule. And I'm just going to come on over to the last slide and thank the other members of the chemistry team. It's not, this is definitely a team effort. And likewise, we rely heavily on some open source packages. Yeah, and